Okay, Kaylin asked about the CP value. So we have an equation that is Q is equal to, what we learned first was for solids and liquids, Q equals MC delta T, where C is equal to the specific heat, nobody says this word, but it has another word, capacity. The specific means it's per unit mass here. So heat capacity would be capital C, lowercase c is the heat capacity per unit mass. So this stuff here combined, capital C is equal to m lower c, where capital C is the heat capacity. But this was for liquids or solids. Now, dirty little secrets, just like we were talking about, why can't we agree on what the conversion is between calories and joules? The specific heat we say is constant for water. It's a different value for ice than it is for water, but we say it's constant for water. That's not true, really. The specific heat actually depends on the temperature. So you have the specific heat for water at 4 degrees Celsius is different than the specific heat at 96 degrees Celsius. And we just take an average. I think that the reason people have some differences in the relationship between heat and joules might be related to that. But I don't know why we can't agree still. So that's for liquids and solids. The heat is MC delta T. So that C is defined by this relationship. So basically, people take water and they say, okay, I put this much heat in, how much did the temperature rise? And that's how they determine that value C. And it's a linearization of something that's close to linear. Now, for gases, and I'm going to replace gases with ideal gases. We have only dealt with ideal gases, but it's still important to say ideal gases because real gases are a little different. If you put in heat and you keep the pressure constant, it's going to behave differently than if you put in heat and you keep the volume constant. And so we have two different linearized relationships. We have the heat at constant volume is equal to, and now we do a molar specific heat instead of a mass specific heat. So once again, we're linearizing the relationship between heat and temperature change. But now it's molar specific heat. That's an L. The molar specific heat at constant volume. And then if we keep the pressure constant, it's just like that. Q sub P is equal to N C sub P delta T, where C sub P is the molar specific heat. At constant pressure. And so how do we get those values for CP and CV? We get those by taking the equation for internal energy and the first law. So the first law of thermodynamics says delta U is equal to Q minus W, right? So if I do a constant volume, what do we call a constant volume transition? So if I do an isochore, I have work is equal to P delta V is equal to, what's that equal to? If it's constant volume, what's P delta V? 0. So delta U is equal to Q. But for a monatomic ideal gas, well, for any ideal gas, U is equal to the number of degrees of freedom times 1/2 nRT. right? That comes from the equipartition theorem. And for monatomic, F for monatomic is equal to 3. And so for monatomic ideal gas, U is equal to 3/2 nRT. And you can use capital N, lowercase k, or lowercase n, capital R. Those are equal to each other, so you can write it either way. So if I take this, I know delta U is equal to Q. And now I know that U is 3/2 nRT, so delta U is going to be 3/2 nR delta T, because N is staying constant, R is of course a constant, as is 3/2. And so using that relationship that for a constant volume, that should be equal to NCV delta T. Then we take this equation, we say, wait a minute. If NCV delta T is equal to 3/2 nR delta T, then if I divide both sides by the same N delta T, that gives me CV is equal to 3/2 R. So we know CV exactly here if it's really an ideal gas. When I was going through class, we looked at the actual values for CV and saw that they were pretty close to that. Not exactly that, because nothing's really ideal. So that's the relationship for CV. Now for CR, we just go, or CP, excuse me, not R. Now we go to an isobar. And for the isobar, it's constant pressure, so work equals P delta V. That's not a V. And pressure is constant, so the end. Except for I could use the ideal gas law. Since pressure is constant, P delta V is the same as delta PV, but that's only true if it's isobaric. The second line would be untrue for any case that's non-isobaric. So you want to make sure that's clear, that you don't say, oh, you can just move the delta in and out like that. Only if the pressure is constant. Then using the ideal gas law, and since N and R are constant, I then move the delta back to just the T. So the shifting of the delta in both cases is because if something's constant, if I have delta, this whole thing, the constants can be brought past the delta because they aren't changing. So that gives me, now instead of being 0, work as nR delta T. Again, using the first law of thermodynamics, delta U is equal to, I'm just going to stay for monatomic ideal gas here. 3/2, well, yeah, 3/2 nR delta T is equal to Q minus W. So Q is equal to 3/2 nR delta T plus my W, and the W I worked out was nR delta T. So the heat is equal to 3/2 R plus R. Of course, 3/2 plus 1 is 5/2. And using that linearization, we can immediately read, if I divide everything by N delta T, CP is equal to 5/2 R. So these values in boxes, in the purple boxes, those are the CV and CP, the molar specific heat capacity at constant volume and molar specific heat capacity at constant pressure for a monatomic ideal gas. And now that I've gone this far, there is one more parameter that we define now. We define gamma is defined as CP over CV, which if you take those for monatomic ideal gas, that would be 5/3. That's important for adiabatic processes. I did not establish why you have the PV to the gamma as constant for adiabatic processes, but just since I've done the CP and CV derivations here, gamma you just should throw in there for completeness. Did that answer your question, Kaylee?
Yes. And so if we have to use CP on the exam for whatever reason, should we just memorize straight like it's 3/2R?
Well, it's on the exam. It's on the equation sheet. I've actually reorganized it to make it, I think, more obvious to students. But it says like F for a monatomic ideal gas is equal to 3, and like U is equal to F parenthesis 1/2 KT. So you have to say, oh, that F is the same F. You have to know which F is F, which F. Yeah, they were there, but I've rearranged it so hopefully it'll be clear. And if you can't find it, raise your hand. All right. Only 15 minutes spent on that. The exam, calculus questions. There are 2 categories of calculus questions you can have. Category number 1 is the Maxwell-Boltzmann distribution calculations. Do you guys remember the Maxwell-Boltzmann distribution work? Remember this sheet here? So I have on the equation sheet the Maxwell-Boltzmann distribution. It's also shown on this sheet. And so one thing that you could have would be you're given the Maxwell-Boltzmann distribution and you have to find one of, I'm guessing it's this one here. Yeah. You have to find one of the things that we found on this page here. So it'd basically be reproducing what we did. So what we did here is we found the most probable speed. The most probable speed is finding where you have a peak on that distribution. So if I have a curve and I want to find the maximum value, how do I find the maximum value? General calculus question. If I have a curve and I want to find the maximum, how do I do that? Take the derivative and set it equal to 0, and then you find what the value, in this case of v, is, where the slope is 0. And you can see from the picture, the slope is 0 at the peak. It's also going to be 0 at an infinite speed and 0 at 0 speed. But those are minimum. So you throw out those 2 and you just take the one that's remaining. So that's how you would find the most probable velocity equation for Maxwell-Boltzmann distribution. You could also find the average speed. So the average speed, you just take the probability multiplied by the speed and integrate over all possible speeds. So that is a Maxwell-Boltzmann integral. And so you go back to the page. I will obviously give you that page if we're going to do a Maxwell-Boltzmann problem. You go back to that page and you say, okay, what is this integral that has v cubed out front and then the e to the minus av squared? And so you have to go through and work out that integral to find the average speed. Or I could ask you to find the RMS speed. The RMS, remember RMS means root mean squared. So the first thing you do is you find the average of the squared velocities. So that means you do the integral of velocity squared times the probability. After you do that integral, then you square root it, right? Because that's the root part of RMS. In this case, you have an integral. Instead, it's going to have v to the 4th. Where did I have it? I don't see the word for this. I know we did it in class. But you would have the square root of b integral v to the 4th e to the minus av squared dv. And so you have to look on that table to find what this integral is. And then you plug it in, do the square root, and that would give you the RMS speed. Now notice all of these, you have the answer for them on the equation sheet. So my problem is, if I have actually, the other option you also has all the answers on the equation sheet. So you're not going to have an answer to circle for this. The answers will be known because they're on the equation sheet. It's the calculus and the method of getting there that is all that can be graded. So that's the first thing you could have. Calculation of the most probable speed, the average speed, or the RMS speed based on the Maxwell-Boltzmann distribution. So that's using your calculus skills. Just, I want to review here, especially because you're not really doing the integrals. The derivative, yes, you'll have to do the derivative. The integral, you're not really using your calculus skills per se. You're using this sheet and identifying, okay, so I sub 1 is 1 over 2a. That is if it's v to the 1 power, it'd be 1 over 2a. If it's v squared, which was the first one of the it was actually v cubed, or right, v cubed. So if n is 3, then you have the integral for n equals 3 is equal to 3 minus 1 over 2a. The integral for 1, well, the integral for 1 is here, so you just plug that in. And if it's 4, well, then life gets a little more fun because you have I4 is equal to 4 minus 1, 3 over 2a times I2, and I2 is 2 minus 1 over 2a times I0. So you have to go through the iteration twice for that one. Michael. Yeah, we actually have right here from the class when we did it before, I2 is equal to 2 minus 1 over 2a, and then I of 2 minus 2, which is I of 0. And so then I replaced I of 2 minus 2 right below. I0 is 1/2, right there, 1/2 square root pi over a. And 2 minus 1 was 1, so it's 1 over 2a times 1/2 square root pi over a. That was the example for I2. What was that? Okay, so for I4, go away. So I'm using this equation right here. I4 is equal to 4 minus 1 over 2a times I4 minus 2, which simplifying is, of course, 3 over 2a I2. But I2 is equal to what we had right there, 2 minus 1 over 2a I 2 minus 2, which is equal to 1 over 2a I0. So plugging that in, and then I0, I look at this table. Got to remember, it's pi over a. That's an a on bottom. And so that's what I have for I4.
So for I4,
Yeah, you go through iterations to get down. It's the classic recursive function, or a classic, not the classic. You have a question, Caleb?
So with the n,
Uh-huh.
are we given it or do we have to find it? How do we come about that?
That would be from, okay, so if you're asked to find the average, then you know that the average is equal to the integral of v times the probability, which is the Maxwell-Boltzmann distribution, dv. And this f is this equation in the box. So that F has a V squared. Now, you've got to pay attention to the constants. I've just been using B for my constant, right? You have to pay attention to the constants here. But that F is going to have a V squared. So it's equal to a constant times integral of V times V squared is V cubed. So I'm going to have that form where B and A are constants, which we have to pick up, right? We can't just say B in our answer. We have to match what it actually is. But there I have, this here is the definition for I3 because the power on V is 3. Yeah.
So,
You understand now?
Yeah.
so I get finding I0 and all that, but what is that like? What do we need to? What are we using those for?
We're using those to find the equation for V average or the equation for V RMS.
So that's for RMS. That's not for like average speed. That's just for the RMS speed.
Well, it's for the average and for the RMS. I could give you either one. I would say find the RMS or find the average or find the most probable.
But it would be the same thing.
Well, the V most probable is the one where you are maximizing functions, you're finding the derivative setting to 0.
I meant
The V average and the V RMS is the same thing, except for V average is V times the probability. V RMS is V squared times the probability. Excuse me? So VRMS, the difference in V average and VRMS is equal to the square root of the average of V squared. Right, so I have the square root, that's the R of RMS. And I have V squared here because that's the S of RMS. And I have the integral over all possible speeds because that's how we find the mean. And so it has the added complication of this being under a square root. It's not a big complication, but you do have to remember it. And so now when you put this in, since F has V squared in it, it's V to the fourth. So VRMS is the square root of VI4. You find what I4 is, multiply by V and square root it, and then you have your RMS speed. Well, the square root of V times I4. Yep.
And what is B?
B is going to be the constants you get. So I actually worked it out when we did it here. You have, in our equation, we had this constant out front, right? So that's B.
Is that always B then?
For these problems, yes, that's always B. And A is everything that M is multiplied by here in the exponent except for the minus sign. So A is going to be M over 2KT. Yeah, because it is constant. But you can't just throw that stuff away. In the end, you have to substitute that in for B. It's just I write B instead of putting square root 2 over pi M over KT is 3/2 20 times. It's just a lot quicker to write B until I get to the end and then put it in.
What is constant?
So I didn't write it on here. I wrote it on the other sheet. Here's where I wrote A. And then B is the thing that I circled here. And the only reason we use A and B is to make writing much quicker.
Okay, so just make anything simple. So let's say we get that equation, we find that we substitute the constant.
I didn't follow that because
I just want to
say we're given what equation first?
We're given like a problem like find F, for example.
Okay. Be specific. Given a problem that says find
Find the RMS.
Okay, find the RMS speed. And then you'll be given that the equation for the Maxwell-Boltzmann distribution is on the equation sheet, and it's also on this sheet. You have to know that you're using that equation, right? I'm not telling you to use this equation.
Yes, sir.
You have to know that. And so if it says find RMS speed, then you have to know, okay, RMS means root mean squared, which means I have to do the square root of the average of the velocity squared. How do I find the average of the velocity squared? The integral of velocity squared times the probability of the velocity. And so all of those thoughts have to come through to get the integral that I wrote here. Right, square root of the integral of v squared times the probability. dv. And then after you've identified this is what is the calculation for VRMS, then it's kind of mechanical because none of us can do these integrals. We use that table to determine what the integral is. Okay, that's one of the two types of questions you could have. Okay.
We just talked about the most probable.
Yes, the most probable. The most probable was the first one I talked about. The most probable is when you're trying to find the maximum of that curve. And so given this equation, the equation that's in the box, to find the maximum, I take the derivative of that with respect to speed, set it equal to 0, and find the speeds that I get when I set that derivative equal to 0. And it'll give you 3 speeds, one infinite, one 0, and one that's your answer. Derivative of the Maxwell-Boltzmann distribution. This right here. The Christmas colored box now. On your equation sheet, it will not be Christmas color. Just you know.
Also, will we just be given the equation, or will we also be given this?
You would be given this sheet plus the equation sheet. Yeah, I don't expect you to have this stuff memorized, but you need to know the process of finding RMS speed, process of finding average speed, process of finding most probable speed. Okay, second thing that we could have on the test would be, so calc problem. Option 1 is Maxwell-Boltzmann problems. Find V most probable, V average, or V RMS. That's the first thing you could have. The second thing you could have find the work or change in entropy for a thermodynamic process. For instance, here's one I won't give you. Use calculus to find the equation for the work done in an isochoric process.
I would have preferred that one.
You would have preferred that one, would you? What would your process have been, Trace?
I suppose so. Changing volumes.
Yeah, that would be it.
That's like a fine question.
You think that was fine, do you?
Yeah, that would be great.
You used some hard calculus there? What finding that's the work then. So how do we find the change in entropy?
It is change equal to
So we'd start with ds is equal to dq over t. And now we're like, right? Well, what is dq? If it's isochoric, we already talked about this. This is what Kaylin asked about at the beginning of class. Now, we were doing things in a non-calculus version here. And so we said QV is equal to NCV delta T. Well, in the calculus perspective, that means dq is equal to NCV dt. And notice Q became dq. That doesn't seem right. That's because Q is actually already a change. That's why we often put that slash on the dq to indicate what? Look, dq is what we normally call Q. So in this case, where am I here? That would be equal to NCV dt over T. So how do I find the change in entropy then? From ds, how do I find change in entropy? ds is an infinitesimal change in entropy. How do I find a finite change in entropy? Integrate, that's right. Notice my equation already had the variables separated, so it was real simple. N and CV are constant, so that's just, well, what is the integral on the right-hand side? What's the integral of NCV dt over T? N and CV are constant, that's right. Go ahead, Caleb. Oh, I thought you were. Okay, N and CV are constant. What does that mean we can do, Trace? Pull them out. And then we have the integral from temperature initial to temperature final of dt over T. What's the integral of dt over T? That would be dt. That would be doing something like the derivative. It should go up in power, yes. So this is t to the minus 1. It needs to have something that's on the order of t to the 0 power. This is the one that's special. We don't have t to the 0. What we have is natural log of t. So plugging in my limits, and this is, each calculation by itself is illegal. You can't do the natural log of temperature final because you can't do the natural log of something with units. But if you combine the two, it becomes legal, which is good. Because using the rules of natural logs, if I have natural log of A minus natural log of B, that's the same as natural log of A divided by B. So this is equal to NCV natural log of T final over T initial. Now notice the units of the natural log, it's unitless. That's legal now. So that's how we find the change in entropy. So finding the work for the isochoric process, really simple. Find the change in entropy, we required a little more work. Now that's one of the 4 processes. The other processes you have are isobaric. Okay, go ahead. Adiabatic and Thermal, an isothermal. So we have enough time to do at least one more. Choose one. Isothermal? Okay. So if we do isothermal, work is integral of P dV. Isothermal, P is changing and V is changing. So this isn't just simple like it was for isochoric or like it is for isobaric. What we have to do here is to substitute so we can write this integral so it only has one variable. So what I need is P is equal to some function of, well, I'm going to put some function times 1 over, or some constant times 1 over V. Why do I do that? Because we know if it's isothermal, since PV is equal to nRT, if T is constant, then I can just say P is equal to nRT divided by V. Since T is constant, I can put this in, and now I have something I can integrate. nRT is constant. So what do I do if it's constant, Trace? I'm going to Trace because he was the first one to identify this before. Well, the V is changing. It's the nRT is constant. So what do I do with the nRT part? Yeah. And then, as Nate said, it's natural log. We just did it with T's a second ago. Well, a minute ago. So I'm going straight to the quick of it because we just did the long of it. And so there's our equation for the work for an isothermal process. It's not super hard, but you have to remember, oh, I can't integrate with two variables in the integral. I need one of them. And so I had to find a way to change P so it was just a function of volume. So that's finding the work for an isothermal process. What about the change in entropy? Going back to what Nathan told us, that's dq over T. If it's isothermal, what is dq? That would be adiabatic. Adiabatic is heat is 0. Isothermal is the temperature is constant. If the temperature is constant, if it's an ideal gas, I think I have this. Oh, I had it up here. I'm just going to go back to where we have it. Where did I write it? I know I wrote it somewhere here. Here. The internal energy is 3/2 nRT if it's a monatomic ideal gas. So if the temperature is constant, how is the internal energy changing? If internal energy is 3/2 nRT, if you have a constant temperature, how does the internal energy change? Well, we're constant number of moles for everything we do in physics. It's not changing. And so for our isothermal case, we have du equals 0 equals dq minus dw. So that means that we're going to have dq equals dw. So that's dw over t. Well, we just did the whole work thing. dw is p dv. And then since we already just did the substitution that P is nRT over V, notice my T's are now going to cancel. And so ds, well, I should have put it here ds instead of delta s. ds is equal to nr dv over v. Well, now we can do this integral like snap. We've already done it. So there's the work to find the work and the change in entropy for our isothermal case. Now I'm going to choose adiabatic for the last thing I'm going to do here because that's the most demanding one. Adiabatic. What does adiabatic mean?
No.
Q equals 0 as far as we're concerned. We'll put dq equals 0. And we have p v to the gamma equals constant. Let's start with easy. Delta S is equal to the integral of ds, which is the integral of dq over t. If dq is 0, what does that give us? If dq is 0, what does this integral give us? Gives us 0. So the change in entropy is real simple for the adiabatic. But then we have the work. P changes and V changes in an adiabatic process. So now I need to once again find P as a function of V. But remember, in an adiabatic process, not only are P and V changing, so is T. So I can't just use the ideal gas law because T is changing as well. But what I can use is that relationship that says PV to the gamma is constant. And so for this case, my PV to the gamma is equal to P initial, V initial to the gamma, right? Since it's constant, that has to be true. And so then I can write P is equal to P naught V naught to the gamma over V to the gamma. Substitute that in here, and I have my work is equal to the integral of P naught V naught to the gamma dV over V to the gamma. I prefer to write it this way so I don't mess up. Remember our first assignment, we did some of that, taking 1 over v to the nth power is equal to v to the minus a. I do that so I won't mess up the integral. What's the rule for the powers of this integral? When you have a variable raised to the nth power and you take the integral, what do you do to the power? Raise it by 1. So that's going to be v to the minus gamma plus 1. And then we have to divide by the new power. I'm mixing initials and zeros. You know V0 and VI are the same thing, right? I'm so sorry I mixed those. So putting in my limits, there I put in my limits. Now, if you do this, you can leave it like that, and that is correct. But you can simplify it by bringing the V0 to the gamma inside. Well, the P0, V0 to the gamma inside, so I can make this I'm going to bring the 1 minus gamma to the outside. And inside I'll have let's start on the right. What do I have when I have v to the gamma times v to the 1 minus gamma? What do I do in that case with the exponents? I have x to the 5th times x to the 4th. What does that equal to? You add the exponents, the x to the 9th. So that's what we'll do here. We add gamma to 1 minus gamma, and we're left with v to the 1, right? Remember, P0, V0 to the gamma is equal to P final, V final to the gamma because it's constant. So I'm going to change these two zeros to finals, and I can do the same thing now with the first term. I know you said okay, but I can't stop now. I made that substitution. And so this process now is just to simplify it. Now that is much simpler. Now since gamma is always bigger than 1, I prefer to write this as reversing the order on top so that it's going to allow me to put minus on bottom and have gamma minus 1. I prefer to write it that way. So this is my preferred way of writing. It would be correct if you had stopped right there. So what you probably noticed from all of the ones we've done, one version was simple. Right, we found the work and we found the change in entropy. One was simple and one was complicated. Hot tip, I'm not going to focus on the simple. So this is the other type of problem you could have on the test. So your two types of problems would be I was wondering why my pen looks so thin. I zoomed out so I could see more, and then I started writing the same size as normal. So if you look at my writing on here, it goes from small to big. My pen size stays the same. That's why it was looking more wispy as we went on. So we have the two types of problems. Yeah, the writing there compared to the writing there. Two types of problems we have, the Maxwell-Boltzmann distribution type or this type. We're out of time. Any last second questions, queries, or comments?
So, if we were to get the second type, we would be either isothermal or adiabatic, one of those.
Yes, that's right.
And then of those, do we have both find work and change in entropy, or do we just find one or the other?
It could be both, could be one, could be the other.
Okay.
It could be, if it's both, it's really not that much harder because always one is easy and one is hard, right? Or hard is a relative term, but one is easy and one is not easy. It's just going to be find the equation. Whether it's the Maxwell-Boltzmann or this, it's just going to be find the equation. The equations are already on the equation sheet, so you're not going to circle the right answer because they're already on the equation sheet.
So in the case of finding or dealing with the adiabatic isothermal entropy and work, those are given on the equation sheet. So if you our work, our final answer is the same that would be good.
Well, assuming your work is correct. I mean, it's always possible to have wrong work, and then since you have the right answer, put the right answer.
Okay.
But if you do work that you believe is correct and you get to the right answer at the same time, I feel reasonably confident.
Okay.
And so this one here, remember, if you just get the right answers, then I'm just going to give you the credit on them, except for this one here because the right answers are already on the test.
Just have to give the explanation.
Yeah.
So with that one, you want concept, equation?
Yeah, so the concept is reasonably minimal here, and I will tell you what I want for a figure, I believe. So there's not a question of, how do I draw a figure for this? All right, I'll see you in an hour and a half. You will be coming, Trace, right? Since you don't have lab, just want to make sure to remind you.
I'm interested. One last question.
Yes.
Am I allowed to die before the test?
What?
Am I allowed to die?